So lecture 4 week 4. So can you tell me what is your doubt?
Yes, sir, around 6 minutes
6 minutes.
in the. Yeah, yes.
The name is positive feedback.
No, sorry, introduction to positive feedback.
Yeah,
Uh, I'm saying it according to the numbering given
that
in
is
the board.
that is a basically integrator. That one, na?
Yeah, yes, sir.
Okay. 6 minutes.
Yeah, yes, sir. The
Okay. Tell me what
derivation
is your
part.
doubt. Tell me what
Yes,
is
sir.
your doubt.
So, could you derive it once, sir, the
Yeah.
expression?
So this is my integrator. This is my circuit. Negative, positive, positive is complex. C, C plus minus so R. Okay. So if I say this is the V minus voltage, this is the V plus voltage. So V plus is equal to V minus is equal to 0. Why? Because it is a negative feedback. Okay. A negative feedback, to solve the negative feedback, what is the best way? We are taking the virtual ground concept. That means the voltage at the positive terminal is equal to the voltage at negative. Okay. Now if through this R the current I will be flowing. So what is the value of I? I is equal to V1 minus 0 upon R. V1 minus this V minus. V minus is 0, so V1 minus 0 upon R, that is the V1. Now the current who is coming, which is coming from this particular leaf, will be going with this. Okay, will be going with this way. Why? Because it is a virtual ground concept. That means no current will be going inside the operation. Okay. Now, if the current is going with this direction, so what is the value of current? V minus minus of V out upon XC. Okay, or I can say that if it is a capacitor, the current flowing from the capacitor I is equal to 1 by a C integration of VDT. Okay, so the current I is equal to 1 by C integration of VDT. What is the VDT? VDT is nothing but minus V out.
Sir,
Yeah,
here the I and C, I and V, are they interchanged? I mean, the V equals 1 by C integral I dt, right?
Q is equal to
I equals C dV by dt.
C dV by dt. I is equal to V is equal to C 1 by C integration of I dt. V is equal to 1 by C integration of I dt. Okay. Now V is what? The voltage from this point to this point. So V is nothing but V minus minus of V out. That is the voltage is equal to 1 by C integration of. Okay. So V out is what? Minus 1 by C integration of. And what is the value of I? Vi by R. So V out is equal to minus 1 by C integration I Vi upon R. R is a constant, so minus 1 upon RC integration of. Okay. So output voltage is nothing but behave as a integration part of the input. So that's why it is called the integrator.
Yes,
Okay.
sir.
Now if I take the Laplace transform, so V out of S is upon V I of S, or V out of S is equal to minus 1 by RC. Integration is 1 by S, and Vi, the Laplace transform is Vi. So V out of upon S minus S prime RC. Okay. Now it is clear. Any doubt?
Yes, sir.
Okay. If you want to check the frequency response of this one, V out is equal to V of S into minus 1 upon RC. Now for the lower frequencies, when omega is become 0, that means S is also 0. Why? Because S is equal to 0. If I am taking the complex, imaginary term, if I also consider the real term, so S is equal to sigma plus 0. This is the complex one. Okay. For the Laplace transform, what we consider? We consider that sigma should be 0. So S is equal to 0. Now if S is 0, omega is 0. Okay. Now if S is 0, so output voltage is what? Maximum.
Sir, for
Yeah.
Fourier, we consider this sigma as 0, right?
Yeah. For the Laplace transform, we consider the sigma is 0. If you remember, if you basically Laplace transform already covered now.
Yeah, yes.
Initially, if you also cover the Fourier transform,
Yes, sir.
so what is the relation between the Laplace and Fourier transform?
Yeah. Here, this Fourier transform sigma is 0.
Yeah.
It is in, but the Laplace transform sigma can also be
We are
the
we
same.
are putting the value of S. We are putting in the form of S. Okay.
Yes.
So we are saying the S is equal to sigma plus j omega. Okay. And now if I am taking only the frequency effect of this one, okay, frequency effect of this one. So what I should do, I just taking the sigma is equal to only the frequency effect.
Okay, sir.
Okay, generally it is not done. This is the difference between the Fourier transform and Laplace transform. But if I want to see only the frequency effect, so what should I do? I just put sigma is equal to 0, so that is S is equal to 0.
Yes.
Okay. Now if omega is 0, that means S is 0. If S is 0, so this particular term will be infinite.
Yeah. Yes.
That means output is infinite.
So for DC, it will give infinite.
Yeah. Okay, that's why the capacitor, if you remember that, the what is the value of Xc? X is equal to 1 upon j omega c, or we can say 1 upon Sc. If the value is DC component, if it is a DC component, so omega should be become 0. That means Xc should be behave as a open circuit. Remember
Yeah, yes.
DC behavior of the capacitor and inductor. So capacitor behave as a open circuit for the DC. So that means it will behave as a no current will be no DC current will be passed from that.
And sir, likewise, the Bode plot.
Yeah,
Could you also draw that for this, please?
yeah, sure, sure. So basically, we draw the border plot for the between the V out upon V in and take the magnitude of this one. So it 1 over omega RC. Okay. If I take the 20 log, so 20 log of V out upon V in is equal to so this is my value. Here I put the value of omega is equal to omega. So not omega, log of omega. Okay. Now if omega is log of omega is 0.1. Okay. Because if you remember that body plot will never start from the zero. It will start from 0.1 or 0.01. Okay. So what is the value of log of omega is 0.01. So omega value is 10 raised to power 0.1. And what is the value of 10 raised to power 0.2? So it is around 1.2. Okay, or I say the omega is almost 1. Okay, so this is the first point where log of omega is 0.1. Now, if log of omega is 0.1, so what is the magnitude of this one? 1 upon RC?
For omega also.
Yeah, omega is 1, or the log of omega is
Yeah,
0.1.
1 by hours. Yes.
Okay. Now, at what particularly value it will be cut? That means this particularly magnitude. What magnitude?
Yeah.
V out upon V in should be become equal to 1. That's why 20 log n V out upon V in becomes 0.
Yes.
Okay. And if V out upon V in is equal to 1, that means 1 is equal to omega RC, and the omega is equal to 1 upon RC. That means if I
Mm.
put the value of omega is equal to 1 upon RC, it will be cut the this line.
Yes.
Okay. So if I meet this one, so this is my goal. Okay,
Yes, sir.
this is the good. Any doubts?
Sir,
Yeah.
in the same, around the same time, professor says something about open loop integrator. What it means and where is it
Open,
used?
open loop integrator. At the
Uh,
same time,
yes, sir, around the same time. I'm not sure about the exact time. I think if the capacitance is of infinite value or very, very large value, then it can be, it is possible to use it on the as a open loop integrator.
where okay, capacitor value is infinite or very large. So basically, the reason is that if I am talking about the V out is equal to 1 upon RC minus integration of VI. Okay, so it will be value will be infinite or basically the open loop when 1 upon RC becomes okay, or approximately towards the G. Okay, RC towards the zero. Not exactly zero. Why? Because if it is a zero, so we can say the V out is because zero multiplied by anything is zero. But if this RC tends towards to zero, but not exactly zero, so we can say V out is equal to mm, integrator VI. That means integration is possible, but the RC value is very very less. Okay. Now if RC value is very very less, so what is the meaning is that R value is very high, okay, and C value is high, okay. If R value is high, what is the gain? So minus RF by R. If I am removing the capacitor, okay, if I am removing the capacitor, so if R value is high, the gain is voltage gain is 1 minus RF by R1 because it is a non-inverting amplifier. Okay, so if R gain is minus RF by R1, and if R1 or we say the R is very high, so the gain is very less. So the one condition is that it is not possible that we can put the value of R is very high. So the second scenario is that we can put the value of C very high. Okay, so we just put the C value is very very high. Okay, C value is C is so that it's make 1 upon RC become almost G.
But sir, when we add the capacitor, uh,
Mhm.
we are removing the feedback, right?
When we add the capacitor,
We are removing the feedback for DC.
yeah, exactly.
Okay. So if the capacitance is not so large,
Mhm.
should we add another resistor just for DC component so that it
Mhm.
can also have feedback?
Okay. Yes, we can do that also.
Then will it affect the whole circuitry? Because as we are adding one more capacitor in parallel, so that because it will AC will also go through in that side. or should we use inductor to cut
Actually,
off this?
if we use the inductor, so basically the operation is same. If we use the inductor, the operation is same. It will be behave as a similar to the differential.
Um, yeah, yes. Okay. Yes, sir. So as per this diagram, we are actually cutting off DC. So we are not
Which one?
using,
Capacitor.
uh, in this integrator.
Yeah.
So we are not worried about the case that the DC
Uh,
doesn't have feedback.
basically, yeah. Basically, if we provide the DC, so like for example, if my input is become a DC, like for example, I am taking the value of one. So, like for example, I am using this in my input signal. Okay. So, can you tell me what is the output?
Output of an integrator, sir.
Okay. So, for the slope, for the step signal, it will be ramp signal.
Yes.
Again, it will be reducing, so it will be like
Yeah.
this one, this one, this one, and so. So, this is the output. Okay. So, if we are providing the 0 or we are providing the 1, because of the configuration of 1, we can say the 1 integration of 1 dot dt is nothing but t. Okay, like I provide the input voltage Vi is equal to 5 volt. What is the output? V out is equal to minus 1 upon RC,
And see.
integration of 5 dt
Yes.
minus 1 upon RC, the integration of 5 dt is 5
D.
over t.
D. Yeah. Sir, in this
Hmm?
integration graph,
In the
the
integration,
graph,
okay,
the after rising, shouldn't it stay constant?
for this particularly,
Yeah, yes, sir. Because the
basically if I draw particularly this particularly function, so what is the value of this one? Ut minus u of t minus 1, 0, 1, 2.
yeah,
What is this? What is this one?
yeah, this is ut minus one.
Okay. The
Oh,
integration of ut is rt,
ramp.
the integration of ut minus t is r of t minus 1.
Yes.
So this is the rt signal.
Okay.
At 1, it is the rt minus 1. Again, if I add this signal, one more signal, so it is plus u of t minus 2. Again, at 3, it will be reducing, so minus of u of t minus 3. Again, it is a plus t minus 2 minus r of t minus 3. So again, this one plus this one and that.
Yeah, yes, sir.
Okay. Is any other doubts?
Sir,
Hmm.
could you explain the concepts of band gap voltage reference?
Band gap voltage reference, that is in the part of schematic. The concept in this one, no?
No, it's an in diode thing, like N diode and single diode.
Band gap voltage reference.
Lecture 2.
I have no idea about it. Let me check. Yes. So basically, it is it is related to the VPP. Yes, can you tell me basically what is your doubt in that when we are going to the I will explain this thing or what is your doubt? Just tell me.
Explain, sir, explain this thing. The just
Okay.
brief.
I think this is the basically if we are using the one diode and if we are using the multiple diode, this is the same concept. Yes or no?
Yes, sir.
So basically, what we do here is that if you remember with the previous lecture, so in the previous lecture, what we are doing that we are getting the voltage. What is basically the current diode current ID is equal to Is e raised to power Vd upon Vt. Okay. Somehow the relation is little bit if you see in some books, so it is the ID is equal to Is e raised to power Vd upon Nvt minus 1. This is the relation. Okay. But if you taking this one, so the value of n is dependent on the type of material. For the silicon, the value of eta is 2. For the germanium, the value of eta is 1. Okay. And one is negligible. We can neglect this one if we are taking the approximate. So that's why ID is equal to Is e raised to power Vd upon. Now if I calculate the value of Vd, so what is the value of Vd? Id upon Is, taking the logarithmic, so ln is equal to Vd upon, and Vd is equal to Vt ln Id upon. So now we say that Vd is equal to Kt by Q ln Id upon Is. If I increase the temperature, Vt is increases, okay, but as well as the Id is decreases. Id is decreases. So with the temperature, there is a effect that Vd will be reduced. Okay. And what? How much it will be reducing? It is reducing minus 2 millivolt per Kelvin. So if I increase the temperature of 1 Kelvin, it will be reduced to the minus 2 millivolt. This is the value of Vd. Okay. So basically, if I am using this diode in my operation amplifier, like for example, operation amplifier, this is my operation amplifier, and I want to use as a single supply. So this is a plus 10 volt, this is a ground, okay. And for the single supply, I require the VDD value in the positive terminal, and at the negative terminal, I am provide the Vi and then VDD by 2. So if I used to provide this VDD by 2 with the help of diode, like I just use a diode that will provide me the VDD by 2. So there is no need of the battery, separate battery. I can put this my diode and it will be behave as a VDD by 2. Clear? Any doubt? Okay. But
Sir,
what is the problem? Yes, sir.
in VD expression, where you increase the temperature and VT also increases, at that
Yeah,
point, how sir,
yeah. I just
ID
tell
also
you.
decreases?
Basically, if we increase the T temperature, okay. So if we increase the temperature T, that means the voltage VT voltage will increase, thermal voltage will increase. Okay. So we know this one. Okay. Now, but what is the scenario is in that if I increase the temperature, so due to the temperature variations, my electrons movement will be become scramble. Like if in a device, in a semiconductor device, in my device, I provide the voltage. Okay. So due to the voltage, the electron will be flowing in this way. Okay. So this is the value. The value of current will be this one. Now, if I increase the temperature, so what will be happen? These electrons who are moving in a one direction, now it will be having the energy because of this temperature, and the variation, the movement of these particularly electron will be now in a scramble mode. That means some electron will be going in the upper direction, some will be downward, some will be this one, some will be this one, some will be this one. Okay. So that means the electrons movement is now a scramble, in a scramble. And if the electrons movement are in a scramble way, so the value of current, forward current ID will be decreases. Okay.
Yes, sir.
So my temperature will be increase the VT but reduce the ID current. So the effect of these two will be a reverse direction. If I say the temperature is increases, the temperature is increases, that means see this value is increasing and this value is increasing. That means overall VD is increasing. But the scenario is now different. This will be increases, but this will be decreases. Okay, this will be increasing, but this will be decreasing. And the value of temperature increases will create a more effective in the case of ID. Why? Because this temperature variation will be multiplied by 10 raised to power minus 20. So if I increase the temperature of 10 degrees, 20 degrees, 30 degrees, so it will be multiplied by 10 raised to power minus 20. Divide by 10 raised to power minus 19, that means overall is 10 raised to power minus 4. So if I increase the temperature 20 degrees, so the effect of this particularly parameter is 20 into 10 raised to power minus 4. Why? Because KYQ is in the terms of 10 raised to power minus 4. So 20 into 10 raised to power minus 4 is the variations because of temperature increase in the temperature of 20 degrees Celsius. But this ID will be decreases. ID will be decreasing, and the effect of this one is in that higher than this component. So overall, the VD will be decreases. Clear? Any doubt?
Yes, sir, clear.
Okay. So if I draw the curve between the VD, basically VD and temperature, so my curve will be like this. This is the slope, and the slope is minus 2 millivolt per Kelvin. As we increase the temperature, my VD that will be. Okay. Now, if I use diode for providing the VDD by 2. Okay. So what will be happen? Yes, if I use this diode for providing the VDD by 2. So the problem is that if temperature will be varied. the value of Vd will be there. That means if I am working in a AC environment or if I am working in a 45-degree temperature environment, so in the both scenario, the VDD by 2 is different. Why? Because it is a temperature. And we can't sure about the temperature will be constant throughout the year. Maybe possible the temperature will be 0, maybe possible the temperature will be 1, and maybe possible the temperature will be 50. So we can't say that the temperature will be constant. If temperature will not constant, so that means my diode voltage is not. So what I do, I just create one to eliminate this effect. I just add up one. What is the this one in the called the VPT PT80, sorry, proportional to absolute factors. Okay, so we just add one particularly component. The slope of these two this particularly component is 2 milliwatt per Kelvin. So one particularly component having the slope of -2 and one having the slope of +2. So overall the slope will be okay. So this is the concept. This is the concept. Now, how we basically use or how we basically add the 2 millivolt per Kelvin slope. So for this particularly reason, we are going to the band gap voltage concept. Principal concept. So in the particularly band gap principal concept, what it is saying that if I use a one diode, if I use a one diode in place of this one, I will use a diode. This one, and this one, and so on. N number of diode I can use. Okay, N number of diode I can use. So the VD voltage having a slope of -2 millivolt per Kelvin. If I add this component with VPPAT, so we are getting a voltage that having the slope of 0 millivolt per Kelvin, and I use this voltage. Okay, so if one diode will be having a voltage drop of V01, this one is having a voltage of VB1, VB2, VB3, and VB. So we have a multiple diodes that are connected to that. Okay.
Yes, sir.
Now, if one diode that are connected in the basically connected, so voltage VD1 is nothing but VT, or Professor is writing at the 5T. So, so it is like called as a 5T along I1 is basically I1 is basically the current, then one diode is used. Okay. Now if I am using the multiple diodes, so the overall current is IN. Why? Because with the every diode the current will be going as I1. So first diode the current is I1, and the second diode the current is I1. The third diode the current is, and all particularly configuration are in parallel. So that means the voltage is the same, but current should be different. So if I say the from the end diode, the current will be going the I1, 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 I1. Every diode are identical, so the current is I1, I1. So I can say that it is the current is N I1 or sometimes it is the current I2. Okay. So if VD1 is the voltage because of one diode, so VDN equal to phi T ln IN upon I. Now phi T is constant because it is dependent on temperature. There is no relation with the either we are using the one diode, two diode, and second the phi sorry IS. IS is the saturation current. It is not dependent on the how many diodes we are using. It is dependent on which type of diode we are using. Okay, so I1, phi T and IS are these two component is not dependent on any parameter, but rest VD1 and I1, and similarly VDN. And okay, so these particularly two parameters that will dependent on how many diodes we are using. Okay, any doubt till now?
No, sir.
Now, if I say that I n is basically the current of all diodes. So, if I calculate the current of one diode, so what is the value of current in one diode? I1 is nothing but n types of IN is nothing but n type of I1. So, if I calculate the current of I1, I1 is nothing but IN upon n. Okay. So, I am taking the IN upon n. So, V T N by 3 ln IN upon n. Right? So, that is all. I think professor take the total current is I1. The second. Professor take the total current is I1. The current in this one is I1 bar. The current in this one is I1 bar. I1 bar. And I2. So it is nothing but okay, so this is the value of VD1 and VD2. Now, if I subtract these two, so VD minus VD, the value is phi t ln minus phi t ln I1. Okay, phi t I can take it ln I1 minus. Sorry, it is phi t common ln I1 is minus I1. Should hold for 1 minute. Hello.
Yes, sir.
Yes, sir.
Yes. Yes. So, okay, so phi t ln I1 upon is minus ln. Now ln A minus ln B. What is the value of this one? Ln of A minus ln of B. That is ln of A upon B. So I1 upon IS upon I1 upon NIS. So IS cancel out I1 phi t ln. That is B D1 minus B. Okay, now what is the value of phi t? Phi t is equal to KT by Q. If I consider temperature is 300 Kelvin or 298 Kelvin, that is all up to you. So the value of phi t is 1.38 into 10 raised to power minus 23 into 300 divided by 1.6 into 10 raised to power 10 raised to power. 4,
Around
20.3,
25.8.
yeah, around 25.8 millivolts or 26 millivolts. Okay,
25.8, right, sir? Or
20,
5.8.
yeah, 25.8 or 26.
Yeah,
It
26. Yeah.
will depend on the temperature.
Yeah, yes.
So if pi t value is this one, so can I take this one or BD 1 minus BD and equal to 25 BD plus 25.8 millivolt multiply with 11. Okay. Now if I take the differentiation here, BD 1 minus BD with respect to t then. So it is K upon Q ln. Okay. And d by dt of remaining term is constant, only t is variable. So we can differentiate this with respect to t. So this one becomes 1. So it is d upon dt, d d1 minus d dn is equal to k upon q. ln. What is this value? K is 1.38 into 10 raised to 1 minus 23 upon 1.6 minus 8 so it becomes one point three so 0.86 into 10 raised to 4 ln n, and you can see that 56.25 micro microvolt multiply by the. Okay, what we can do here is one more thing is that kt by q ln of n upon t. Kt by q is already known, that is 25.8 millivolt upon 300 Kelvin. So values is nearby almost. So multiply by 56 microvolt per Kelvin. This is the value of d by dt of d d1 minus. Okay, any doubt?
Sir,
Yeah.
why you divided by t in
Basically, we
second
have
last
to take the
question?
differentiation. No? We have to take the differentiation. No? Like if I differentiate k t by q l of n, if I take the differentiation of this one, so what will be? This is the k by q ln of n. Okay, any doubt?
No, sir.
If I multiply t and divide t, is there any effect?
No, sir.
So numerator term is kt by q ln of n upon t. Why I multiply and divide? Because I already know the value of kt by q. We don't need to require calculate the value of kt by q. We have already known the value of kt by q. Now kt by q value is known. Divide by t.
Yes, sir.
So that's why we divide and multiply by t. Any doubts till now?
No, sir.
Should I explain this further? Should I explain this one further? That's okay.
Okay, sir. Okay. It's okay.
I think there is a that your doubt that why we use this multiple transistor. This is the I think only doubt why we take this. Yes or no?
Could you repeat, sir?
I think you have a doubt why we take the multiple diode in a parallel combination.
Yes, sir.
We are using the parallel diodes because if one diode will fluctuate because of temperature, so that particularly value will be compensated with the other diode. Okay. Then if you go in the particular last part of this one, you can see the if I put we are generally chosen the value of n is 8. Why 8? Because this is the configuration of 8. 4, 5, 6, 7. This is the configuration of 8 diode we are using. Now if I am using the one diode in this way, so there is the effect of this diode is very less. Temperature effect of this diode is very less. Okay. So like if any particularly thing or any particularly atmospheric condition will be initially effect of these particular diode, outer side diode. Okay, outer side diode. The effect on these diodes is high. The effect on the central diode that are in between these particular diodes combination, the effect on this one is less. Okay, so if temperature effect is less, so we can say this particularly center diode will provide me the constant voltage that is less effective with the respect to the temperature. So basically, whole concept is only to explain that how many diodes we are using. So in the center diode will be having the less. Okay.
Yes, sir.
Any other doubts?
Sir, could you explain the Smith trigger also?
Schematic trigger. Okay.
Yes, sir.
So basically, what is the schematic trigger and why we use? Any idea if you see the lectures?
So, sir, Smith trigger is a comparator with hysteresis, right?
Compare the
with the hysteresis
okay. And why this hysteresis is required?
to avoid noise in the input,
What?
to avoid the amplification of the noise.
The basically in the negative feedback, what we do?
Yeah, we
We
virtual.
the first condition is that we are taking that V positive is equal to V negative
Yes.
for the virtual ground. Okay, if it is a virtual ground condition, we can say no current going inside the fan. Okay, we can say all current passing through outer feedback circuit. But what about the positive? The positive feedback, no virtual ground. If virtual ground concept is not there, so how we can identify what is the voltage? So in this scenario, we are taking two consideration. The first consideration is that if the terminal voltage positive is greater than the negative, so the output voltage is directly positive. Which voltage is higher? Either the inverting terminal voltage is higher or non-inverting terminal voltage is higher. According to this one, we are getting the output. The second situation is that if V positive is less than V negative or V negative is higher, so V out is now. If we are talking on any of the point at this point, my V1 is V positive is greater, and this point V negative is greater than. So either if this particular situation will be arrived, so we can say below this one, below this one we are getting the positivity, okay, and after this one we are getting the negative. But the problem is that if any voltage will be changes, like for example, we have a V plus voltage is 5.5 and V minus voltage is 5.6. What is the output? According to this situation, minus V. Why? Because negative voltage is higher. Okay. Second scenario, if V positive is 5.5 and V negative is again 5, then what will be happen? Okay. And after
Zero.
that, we have this. And after that, if V positive is 5.5 and V negative is 5, so again a positive. But if this voltage fluctuation is very less, okay, voltage fluctuation is very less. Like for example, I'm talking about the V 5.5 and 5.6. Maybe possible that it will be the 5.5 and 5.51. So it is not possible that either a zero point zero 0.01 voltage my output voltage is suddenly changed from plus VDD to minus VDD. Okay, so for identify this one, there is particular range is defined. That means if voltage will be lies in this range, so it will be become the output in the become positive VDD, and the voltage will be like in this range. It is called like the basically negative VDD, and in between this range, it is a transition state. Okay, so this particularly all working processes are where we have some saturation voltage. We can say that we have some uh, boundary voltage. Okay, in this scenario, my transition from the positive VDD to minus negative VDD will be done. Okay, my particular transition from the positive VDD to negative VDD will be done. And this particularly transition will be defined by a graph, and that is called the hysteresis. Okay, so what it say, like I have a V plus is 5.5. Now it will be decided that if V minus is 5.8, we are getting V out as a minus VDD. If V plus is again a 5.5 and V minus is 5.2, we are getting the V out as a plus VDD. Okay, and in between these, where V minus change from minus, oh, sorry, 5.8 to 5.2, it is called the transition state. Okay, getting my point?
Yes, sir.
Okay, so basically, Smith figure defines the that particularly hysteresis, and that hysteresis tube is used in the negative supply to identify that what is the range where the transition will be done. So that all will be calculated using the schematic. Okay,
Yes, sir.
so if you know that this is the hysteresis tube. Okay, so basically this is called the this particular event is called the transition, where it will go from 0 to 1 or 1 to minus 1 to 1 or 1 to minus. Okay. This is the case where minus VDD voltage is getting. This is the case where plus VDD voltage. This is the you remember I think you particularly cover in the physics part the magnetic materials, type of magnetic materials and the magnetic properties.
Yeah, yes, sir.
There are the different type of material, diamagnetic, paramagnetic. Have you heard this one?
Yeah, yes, sir. We have heard
Okay.
hysteresis before.
Okay. So that is also, if you remember that this is the BH curve is drawn for the magnetic materials. Again, that is the high series. So similarly,
Yeah,
it is
only the
also
shape differs.
yeah,
The shape
yeah,
differs.
shape, yeah, shape. Shape is somehow
Curved
this.
structure.
Shape is somehow this.
Yeah, yes.
So basically, again, this is a particularly graphical. This is basically curve form, and this is a straight line form. Where we are getting the higher voltage. This is the higher voltage. So this is particularly the range. This is the range where transition will be done. After this range, it will be constant. After this one, it will be similarly. Okay.
Yes, sir.
I think that is enough for the schematic.
Sir,
Professor, yes.
yeah. So this hysteresis window,
Mhm.
how is it controlled or how is it made in the first place? I mean, how the comparators diagram is shifted into the hysteresis in shift spin trigger by
Uh,
adding what components
wait. What
in
professor will be
order.
covered? In by basically video, you are talking about the video.
Yeah, yes, sir. I mean,
Okay. Yeah. Yes. So basically, if we are talking about the concept, the professor will be telling that okay, this is a circuit. This is a negative V two voltage and the positive and then okay. Now, what particularly voltage we are getting, that is dependent on two terms. This one V2, and if I am saying this is a V1. Okay. So this V1 voltage is nothing but if I take because of this one, this is behave as a feedback circuit. The work of this particular resistance is feedback circuit multiplied by the VDD. The
yeah, yes, sir.
voltage V not VDD, we can say the V out.
Hmm.
So this V out voltage is going in the feedback part, and we are getting the V1 voltage. Okay, so the feedback component is very important. Without feedback, V1 is no, we are not getting the V1. If we are not getting the V1 or V1 value is zero, the particularly circuit will be now converted to the which one?
I mean, the,
V2. We are getting a zero voltage.
then minus.
What is the value?
So V2 is positive, right, sir?
Yeah, V2 is positive.
Then yeah, it will go to minus extreme,
Yeah,
minus
minus
VDD.
V. Okay, so it will be remain constant. Why? Because there is no feedback, and we are getting the feedback. We are having the feedback, but the voltage is zero, so it will behave as a no feedback circuit is there. Okay, so this feedback component is very important. Now, how we get the feedback component? Feedback component basically the voltage drop at this point. So how we get the feedback component? The VDD voltage, V out voltage will be passing from the out R1 and R2 resistance.
Hmm. Yeah, yes.
So it is a the voltage drop at this point F is nothing but R1 upon R1 plus R2. This point and this point both are same because there is no resistance, so voltage drop is zero. Okay. If both are same, So the voltage drop across R1 is equal to the voltage drop between these and them. So if the voltage V out is coming as a negative, as a feedback part, so I can say this voltage will be dropped in the R1 and R2. So what is the value is R1 upon R1. Okay.
Yeah, yes, sir.
Now the consideration is that possible that V out should be positive, or possible that V out should be negative. So if V out is positive, or we can say we are getting the positive VDD, we are getting the positive VDD, and negative. The positive VDD point is this one, the negative VDD point is this one. So the between difference between these two is twice of, and this twice of VDD is nothing but twice of V. Okay, so this point the voltage is V1 is twice of R1 upon R1 plus R2 multiplied by the V out, or is it equal to twice of R1 upon R1 plus R2? Okay, so we convert complete circuit in the form of resistance to get what is the basically depth, what is the basically width of the hysteresis. Except this anything you are asking, or this in the same thing you are asking?
Yeah, yes, sir. So
Yeah,
by adding this feedback, the comparator becomes mid-trigger, right?
adding this feedback, the comparator become indicator.
We are giving hysteresis character to this. Is it correct or?
No, no, no. Comparator become integrator because of the RC component, C component.
No, sir. I mean comparator to mid-trigger.
Yeah,
The
it's
hysteresis
not.
property
Yeah,
is
yeah, yeah, yeah.
set of
If you are adding the particularly feedback circuit, so it is become a integrator. If we are not adding the feedback circuit,
uh, okay. So this positive feedback is the reason we have this hysteresis.
yeah,
Ah,
positive feedback we have the reason. Because in the positive feedback we are getting the voltage. One is the plus VDD or second is the minus. Now if VDD is 5 volt, okay. If VDD is 5 volt, so we are getting a plus 5 and minus 5. Now if the transition of the voltage is from plus 5 to minus 5, it will be taking some time. Okay. So that time where it will be changed from the positive plus 5 to the minus 5, it basically the draw the basically draw a curve, and that curve is for the state.
yes, sir.
Just another doubt.
Sir,
Yeah.
I have a doubt in week 3 graded assignment.
Okay.
Last two questions.
Last two questions.
Yes, sir.
Mhm. Can tell me. Yes. How many of you have solved this one? I think most of the having the correct answer.
Sir,
Yeah.
your voice seems little unclear. Uh,
Okay. Yes. Now it's
yeah,
fine.
yeah, now, yeah, now it's fine, sir. Yes.
Okay. Now determine the value of R2 to achieve an AC gain of 50. Anyone can tell this one? Because I think everyone have the correct answer. Most of the having the correct answer.
The eighth question, sir.
Yeah, eighth question.
Yeah, this is okay. The non-inverting gain formula, right? I think
Yeah.
we have to apply that. And
Okay. So AC voltage gain is a 50 ohm. 50. Sorry.
1
Okay.
plus R2 by 10 equals 50.
Yeah. 1 plus R2 by 10 is equal to 50. 1 plus R2 by 10 is equal to value of R2 is not exactly this one. This is 490. 490. Okay. And the next one, determine the largest input amplitude of 1 kilohertz sinusoidal that will result in a distortion-free output. The op-amp saturate if the output attempt to go to the within 1 volt of its supply is. Yes, anyone?
So the output can go up to 9 volts.
Okay. Output
Mm,
can go up to the 9 volts. Why? Because it is a 10 volts.
yeah, yes.
Okay. So output go up to the 9 volts. Now what? If output is 9 volts, yes, what we can do now? Anyone?
So
No?
sir, this is a continuous of all previous questions, right?
Yeah.
Okay. Then
So basically, your output goes up to 9. V out is goes equal to the 9 volt. Okay. As we know that A times V in is equal to V out. And what is the value of A? 1 plus RF by R1. That is, we already calculate RF R2 by R1. Sorry, not RF, R2 by R1. So that is equal to 1 plus 490 upon 10. That is 50. Okay. So A into V in is equal to V out. That implies V in is equal to V out upon V. What is the value of V out? 9.
50.
9 volt.
Oh,
Upon
okay.
A, 50. That is 0. Okay.
Sir, how V out is equal to 9 volt?
Why V out is the now in word? Because it says the statement, it is a statement. The op amp saturate if the output attempts to go within 1 volt of the supply is. What is the supply voltage? 10 volts. Okay, and the output will be go up to what? 1 volt range. 1 volt range, that is the 9 volt to 11 volt. Okay,
Yes, sir.
up to the 9 volt, not exactly 9 to 11, up to the 9 volt. Because if 10 volt is the maximum supply, so it will be lesser minimum maximum value is the lesser of 1 volt with the higher supply, and the supply is 10 volts, so the output maximum should be possible at the 9 volt. If output possible should be maximum at a 9 volts, so what is the V? Okay,
Yes, sir.
Sir,
yeah,
uh, in the last formula which we used, um, why we put A VIN and A V in equals V out and not A differential voltage equals V out?
basically V out upon V in ratio is the voltage gain, AV.
Okay, yeah, correct.
Okay. So that's why V out upon V in is equal to AV. So I can say multiply cross multiply, so A times V in is equal to V.
So, but sir, in op amp, the difference between the two voltages in the terminal is amplified, right?
The difference between,
In the op amp,
yeah.
A V1 minus or V plus minus V minus
Uh, I am just
is
saying the V in. I am just saying the V in. I am not talking about the what is the value of V. V in value may be possible the V plus minus. Maybe the V value, V in value is the V plus value. Maybe the V in value is the V minus value. That is up to the what is the V applied at a V plus and V minus. But the difference between these two is the V.
yeah, correct.
Okay, if I am talking about the voltage gain, so
Uh,
voltage gain is the basically the
oh, okay.
voltage at the input side, and the voltage at the input side is nothing but the combination of positive and negative both voltage.
Okay. So this voltage gain is different from the
Overall
open
gain,
loop
yeah,
gain.
voltage gain is different from the overall gain.
Okay.
Thus,
Mm.
voltage gain is only for the operation amplifier, and that is the circuit of gain. This is for the gain, not voltage gain.
Okay, okay. Yeah, okay, sir. Okay, so we have to focus on the wording also, sir. Then.
Yeah, exactly.
Okay, voltage gain means this AV in equals V out,
Yeah,
and the loop gain or the standard open loop gain means the AV difference equals V out.
yeah, yeah.
Okay, okay, yeah, yes. Okay, sir.
Okay. Any doubts? Yes, any doubts? So, shall we stop here?
Yes,
Okay.
Yes, sir.
So, thank you all.
yes. Thank you, sir.
Thank you, sir. Good night.
Thank you. Thank you. Good night.
Thank you, Shley. Good night.
Good night.